Hello all, welcome to the Linux Rootkits for Red Blue Teams course on Pentester Academy. Now in this video, we will begin with learning how to write kernel modules, and we will look at the customary Hello World kernel module. So let's jump right in. So what are loadable kernel modules? Now, typically on a Linux system, you have user space where all your, user applications are running. And then you have the kernel space where you actually have the core operating system and then the hardware. Now, user applications can only talk to the hardware via the kernel, and the kernel uses device drivers to talk to the hardware, right? Now, as such, the Linux kernel is monolithic, but it is possible to go ahead and write modules which can be plugged in and out of the kernel. And these modules are used to enhance the kernel's functionality. Now, these are called loadable kernel modules, or LKMs as an abbreviation. Now, of course, the LKMs can do a lot. The first thing to realize is, even though we've drawn a very, very simple looking, block diagram, the kernel is very complicated. And we will unravel many of these complications and subsystems as we move along in this training. So how do LKMs actually fit in with, all of the kernel core code? Now, as I already mentioned, the Linux kernel itself is monolithic, and the LKMs allow at runtime to change the behavior of the kernel. Now, the way they do this is by going ahead and leveraging all the core APIs available in the kernel, and at times they might even extend that functionality. So examples of kernel modules are device drivers. So a lot of times on Linux, you would find that if you bought a new wireless card, we go on to that hunt for finding the right drivers and making everything work, right? Drivers are typically LKMs. Now, other examples of LKMs include file system drivers, security products where, maybe you're doing some kind of rootkit hunting, etc., and many, many other possibilities. Now, a lot of times people misunderstand and think that LKMs are almost exclusively used to make device drivers. This is not the case. They can be used to write purely software components in the kernel. And of course, the best example is the rootkits we'll be talking about. Now, the great flexibility with LKMs is, use them only when you need to. So the core monolithic kernel contains all of the extremely important subsystems like memory management, scheduling, and all of that, which are required for the system to run. And optional components, which is basically LKMs, are used whenever we need more functionality. So are LKMs, once they are loaded into the kernel, any different? Are they treated in a different way? Not at all. So once a loadable kernel module is running in the kernel, it's as good as being part of the kernel and has all the superpowers of the kernel. So it can change memory, it can play with processes, can do whatever the kernel can do. Now, as you can see, this means you have a lot of power in your hands, but of course, that comes with a huge amount of responsibility as well. This is simply because of the fact that, a kernel module can completely wreak havoc on a Linux system. Now, because there is no memory protection available, an LKM can very easily go ahead and write to, important parts of the operating system, which may lead to an immediate crash. And that is really why, we have to be very careful when we write them. Okay, so I think we've looked at, the very basics of LKMs. Now let's look at how to write a very simple LKM. Now, we will look into details of, Linux kernel, the processes, and a lot of other architectural complexities. But I like to use like the funneling out approach, where let's start with simple examples, make sure that we can run them, build our confidence, build our excitement, and then slowly start looking at more difficult concepts as we move along. Okay. And that's the reason why I haven't brought in all the low level kernel stuff right away, right? We will do that. There is a time for it. So be patient. Okay. So now let me actually go ahead and shift over to our virtual machine. So this is the same VM we've created in the previous video. I've actually created a bunch of them, but they're all the same config. I'm going to create a directory called class. Change into that directory. Actually increase the font size just a little bit. Okay. I'm going to create my very first directory. It says 001 hello world. Let's change into that directory. Now the first few programs, I'm going to kind of type it in so that we can, have a good discussion. And as we move along in the course, I'm probably going to show you code I've already written, simply because there are going to be a lot more lines. So you can use any editor that you're comfortable with on Linux. I'd actually recommend if you can learn Vim, but again, that's up to you. The only reason I say that is in later videos, when we look at things like cscope, ctags, etc., it's easier to work with Vim than with other editors, but it is possible to work with other editors. Okay, so let me go ahead and now create our hello world.c LKM. So the first thing I'm actually going to do is put in some includes here. So the first one is module.h, and I'm going to go ahead and put in another include, which is going to be init.h. Now I'm going to write out the first function, and then I'll tell you what that means in just a bit. Okay, so when we insert our loadable kernel module into the kernel, then the kernel needs to know what is the first initialization routine it actually needs to run in our module. And this is going to be the initialization routine, and I'm calling it LKM_init. Now, of course, there's no way for the kernel to know that this is the initialization module. So I'm actually going to go ahead and call a special function called module init, and inside that I'm going to mention that my init function for the kernel module is LKM_init. Okay. Now inside this, I'm actually printing the string hello cruel world of kernel programming, not just hello world. You will see why it's cruel as we move along in the videos. Now PR_info is very similar to printf, which you've seen. What it does is it internally uses one of the functions available in the kernel called printk, and in that it's actually setting the log level to information, right? And we'll come to log levels and all that as we move along. Right now, the only thing you can probably keep in mind is PR_info allows us to print this string out. Now, where is this string stored? It actually goes into the kernel messages log or whatever other configuration you might have via syslog, right? But on Ubuntu by default, we should actually be able to see this as part of kernel messages. So let's actually write out another function, and this is going to be the exit routine. And similarly, I'm just going to say, wow, you exited early. And over here, I'm going to mention this. So this is called when we unload the kernel module, right? LKM underscore exit, and we mentioned that in module underscore exit, we call the function and we basically pass this, right? So what really happens is, as soon as we insert the module, this gets called, the kernel module gets loaded, and when we go ahead and remove the module, this gets called. Now, additionally, what you'd find here is I have, underscore init in here and an underscore exit in here. Now, this is a special identifier, and what it actually tells the linker is that as soon as this initialization is done, we are no longer going to require this function. So if required, you can do away with it and free up that memory for other things. So underscore init typically is for functions. You also have something which is underscore init data, which is actually for data you only require during initialization, right? Now, similarly, underscore exit kind of comes in, and again, if this is basically a module which has been baked into the kernel, which is instead of being an independent module, this is actually compiled into the core kernel, then this really has not much value. And this is kind of going to be more important in the other case. So underscore exit is omitted if the module is compiled into the kernel. And if that is not the case and this is a standalone module, then pretty much it doesn't have much of an effect, apart from some basic things happening at the linker layer. Okay. So apart from this, there are a couple of other things we'd like to put in. First is the name of the author. Oops. So we can do that using a macro called module underscore author. Let's say Vivek Chandran. And then after that, we want to give the module license. So I'm going to say GPL v2. This has some significance simply because if you're not using one of the GPL licenses and instead a proprietary license, then many a times the kernel will not allow you to communicate with other modules which are GPL only. And this also, if you kind of don't mention the license to be GPL, ends up tainting the kernel, right? So the guys in the Linux kernel development team, they hate closed source things, and rightfully so, right? If you want to run in the kernel, you better be open. People can fix bugs, people can see what you're doing, and that is desirable. But they do allow closed source modules as well, which is binary modules. But those modules are required to mention that they're using a non-GPL license. Finally, we can also give a very simple description for the module. I'm going to call this Hello World module. Okay. So let me quickly have a look. Just want to make sure there are no typos. Of course, if there are, we'll fix them, but I'd rather not have typos. Now, the next thing we actually want to create is the make file, right? So that we can compile this kernel module. Now, before we do that, we need to know where our kernel source code is. It's actually there inside this directory. There it is, right? Something we created in the last video. And now let's actually write our make file. I'm going to keep this make file extremely simple. Actually going to say we'd like to compile this as a module, and based on the name of the file, need to mention the .object file here. So if the name of the file is hello-world.c, basically have hello-world.o in here. And after that, we go ahead and set up commands to make as well as to clean up stuff. And I'll explain these commands in just a bit. We only have to do this for one. The make file is pretty much going to be same for all the other programs that we're going to look at as well. So don't worry, this painful process is just once. Okay, so as I mentioned, the obj-m, what this mention is, we need to compile this as a module. And the important thing to note is, because when you're compiling a kernel module, we need to refer to the kernel sources. And for most of the latest kernels, you will need to basically have a source tree which has at least been prepared for module compilation, preferably even if you've compiled the entire kernel, right? But at the very least, you must have prepared it for module compilation. So what we need to do is, when we are calling make, we need to make sure that we pass the location of our kernel root directory in the make file, so that that can be referenced and used. And after that, of course, we would want to go ahead and compile the modules located in the current directory. So the identifier kernel underscore root needs to be provided when we are using the make file. So to make this, I'm actually going to say kernel underscore root equals, so home Vivek Linux, and then let's just say make. Hopefully there are no typos. Okay, now if I do an ls here, you can see that it has been compiled. There are a lot of in-between files as well. We don't need to bother about them. The key thing to find here is the hello-world.ko. If you actually do a file hello-world.ko, you'll actually notice it's a 64-bit binary, right? It's an ELF. And if you want to know the information about it, you can use a utility called modinfo or module info and type in hello-world.ko. And if you notice, this now gives us some of those parameters. The description, a hello world module, license is GPL v2, author is Vivek. This is the name, this is the version magic, right? And a couple of other things. Fantastic. So now let's go ahead and insert this module into the kernel. Now to insert the module, the command we are going to use is insmod. Now keep in mind that you can only insert a module as the root user. So if I try to insert this right now, what you would find is that this won't allow you to do it. It'll say operation not permitted. So I'm going to do sudo insmod hello-world.ko. Asks me for the password. Nothing seemed to have happened. But if we do an ls mod, which is list modules, and scroll up, then we would actually see that there is a hello world running here. Also see a hello world underscore FMT. I'm sorry about this. I was testing code for the next video already and looks like this still remained. I forgot to take it out. But anyway, this is the module that we've inserted right now. Fantastic. Of course, you're wondering, what happened to all of those messages? So one way to look at it is to type in dmessage, but of course we'll see a lot of scroll, and then at the very end you'll end up seeing hello cruel world of kernel programming, right? Omit this part, I apologize, this is for the next video. The only thing we need to look at is here, and we can even monitor this live. So if I open up a new terminal, I can do a tail-f var log and actually see where this is, kern.log -n0, so that we can now monitor. I'm going to remove the module. Remove the module from this terminal so that we can see the exit message. Removal happens with rmmod or remove module. Hello world.ko. There, if you noticed, we are seeing that basically there is a message, wow, you exited early. And now if you try to put that back in again, you should be able to see hello cruel world of kernel programming. You can clearly see that. And of course, anytime you remove the module or you insert the module back again, we are going to see this trace back. Fantastic. Now you can set the default log level for the console and be able to see these messages on the console itself without having to look at the kernel message file. And we'll talk about this later when we look at print k and the different log levels. Fantastic. Now, if you want to clean up everything, you can type in make clean and this would end up cleaning everything. May have done a little typo in my make file. Good, that probably caught this right here. Let me just double check everything. Oh, my bad. Everything is okay. I forgot the whole kernel root part. Make clean. And once you do that, you end up cleaning up the entire directory, right? Now, we can go ahead and fix this inside the make file as well. The only reason I'm not doing it is just so that I make you pretty much remember for at least the first couple of video demos that it is very, very important for you to reference the kernel source when you're building the module, okay? So make is to build the module and make clean is to clean up all of these, right? Fantastic. So I hope you enjoyed this video. And if you have, please do recommend Pentester Academy to your friends and colleagues in the InfoSec community. Thank you and have a great day ahead.